Welcome to Lesson 09, the one you'll actually quote in the budget meeting. Compliance gets you the mandate, but performance is what justifies the engineering quarters. And we have 4 hard numbers to prove it. 25 times faster lookups at 10,000 rules, 100 times faster reloads through atomic updates, 60% less memory at scale, and 0 race conditions during reload. By the end of this lesson, you'll walk into that CFO conversation with ammunition, not adjectives. So here's the map for the rest of the lesson. 4 measurements, 4 slides in your business case. Lookup latency, linear scans versus hash lookups, 50 microseconds down to 2 at 10,000 rules. Update operations, sequential rewrites versus atomic transactions, 2.5 seconds down to 25 milliseconds. Memory footprint, 40 megabytes down to 16 at 100,000 entries. And operational concurrency, that 10 millisecond race window during reload, gone. Each one stands on its own as a slide your CFO can read. Start with the first measurement, lookup latency. The shape of this chart is the entire argument. Iptables walks the rule list packet by packet, so its cost climbs linearly. 5 microseconds at 1,000 rules, 25 at 5,000, 58 by the time you hit 50,000. nftables uses hash sets, so it stays flat across the whole range. At 10,000 rules, which is a normal day for an enterprise edge, you're looking at 25 times faster per packet. That's not a tuning win, that's a different algorithm. Here's the mechanism behind that gap. Iptables is a linear chain walk. Every packet compares against every rule until it matches. So 10,000 rules costs you roughly 50 microseconds per packet, and 100,000 pushes you to half a millisecond. At 1,000,000 packets per second, that arithmetic eats your CPU alive, which is exactly why your CDN egress buckles under a DDoS, because the mitigation rules themselves become the bottleneck. nftables sidesteps the whole problem with a kernel-native hash set. One lookup around 2 microseconds, and it barely moves as the set grows from 10,000 to 100,000 entries. Logarithmic, not linear, that's the property that scales to fleet size. Lookup speed is the steady-state win. The second gain shows up during change. iptables restore writes rules sequentially. For a 5,000 rule set, that's 2.5 seconds where your firewall is literally half configured, and any packet hitting that window gets undefined behavior. NFT runs the same load as a single atomic transaction in 24 milliseconds. 100 times faster is the headline, but the real prize is correctness. The kernel sees one switch, old rule set or new, never both. The race window collapses to 0. Gain 3 is memory. Each iptables rule carries its full match metadata as a separate object, roughly 400 bytes apiece. An NFT set entry is a compact hash node, around 160. Across 100,000 IP blocklist, that's 40 megabytes versus 16, a 24 meg delta. On a 4 to 8 gig edge appliance, that's real headroom for another process. And because the working set shrinks, cache misses drop, and your lookups get faster too. The savings compound. So where do those 4 gains actually pay rent? 3 scenarios. On CDN edge nodes, 10,000 rule chains mean every packet pays the linear scan tax. Moving to NFT sets reclaims around 40 microseconds at P99, which at 50,000 requests per second is 2 full CPU seconds back every wall clock second. In Kubernetes, service meshes thrash iptables restore hundreds of times a minute. Atomic NFT transactions eliminate the race window entirely. And at the DDoS edge, streaming 1,000,000 IP blocklist into a live set is something a pure iptables stack simply cannot do. Pick the one that matches your environment. That's your case study. And the reason those gains hold up isn't clever engineering. It's structural. 3 things. Iptables walks a linked list, ON per lookup. NFT uses kernel-native hash sets, effectively O1, and the bigger your rule set gets, the wider that gap opens. Iptables, Restore applies rules one at a time with no transaction concept. NFT commits atomically in kernel, so the race window simply doesn't exist. And because an NFT set entry is just a hash key plus a small value, you fit 4 to 5 times more entries in the same memory. Cache lines stay hot. Lookups stay fast. Better data structures, not just better code. So here's the whole argument on one page. Print it, paste it into the business case, hand it to your director. Notice how the lookup advantage scales. 5 times faster at 1,000 rules, 25 times at 10,000, 166 times at 100,000. That's the O1 versus ON curve showing up in real microseconds. Reload drops from 2.5 seconds to 25 milliseconds, memory falls 60%, and the atomic update window collapses to 0. Every row is one sentence in your justification doc. My numbers are useful, but your numbers are the ones that close the deal. So here are 3 drills to run on your own hardware. 30 minutes for the reload benchmark, 45 for lookup latency at scale, 60 for the atomic update test. 2 things to watch. Test the worst case. Last rule, every packet, because averages hide the iptables tail, and take the median of 5 runs since single runs lie. Bring those numbers back to your justification doc. Now, before you walk into that budget meeting, 5 ways teams quietly torpedo their own case, citing microseconds to a CFO who thinks in SLAs, quoting someone else's blog instead of your own fleet numbers, burying the atomic reload win that ops actually cares more about than raw speed. Comparing a fully refactored nftables rule set against a stock iptables setup, that's not fair, and reviewers will spot it. And forgetting memory savings entirely, which on edge hardware is a direct OPEX line item. Each one is solid data getting dismissed because of how it was framed. And that's the lesson. 25 times faster lookups, 100x reload speed, 60% less memory, and atomic race-free updates, 4 measurements, 1 coherent business case. The CFO now has hard numbers, and you have the receipts to back them. Next up, Lesson 10. We leave theory behind and walk through 4 real migration scenarios: a web farm, a Kubernetes cluster, multi-region, and a legacy data center, end to end. That's the execute phase. See you there.